Hello, good afternoon. My name is Marek Prochazka, and I'm the head of the flight software section at ESA. And I will be talking about the handling software commonality overview of ESA flight software onboard Lunar Gateway. So I've been the flight software lead of iHub, which is one of the modules of the Lunar Gateway provided by ESA. The other co-author, Andrei Oganessian, is flight software lead of another module provided by ESA called European Refueling Module, and also flight software lead of what's called the Halo Lunar Communication System. So, yeah, maybe I should use this one. So, you might know that the Lunar Gateway is a station much smaller than the ISS, but to orbit the moon rather than being 400 kilometers from the Earth, it's going to be 400,000 kilometers from the Earth. And it's a rather complex system, as you can see, composed of a lot of modules provided by 5 space agencies, a lot of suppliers. So there is a lot of flight software out there. So this presentation is basically our lessons learned about how we handle commonality in flight software instances on all of these modules. And also partly what we do with, because obviously there is a lot of complex software interfaces between these modules. So how we handle this complexity. Just an overview of what ESA is doing for Artemis. So apart from providing 2 modules for Gateway, which is what I already mentioned, the European Refueling Module and iHub, which is habitable module. And there is the HLCS, I already mentioned, the Halo Lunar Communication System, which is to provide communication capability with the lunar surface, basically. And we also provide ESM, the European Service Module for Orion. So basically, ESA is part of every single Artemis mission and heavily involved in Gateway as well. There you can see visualization, what are the Gateway elements which are provided by ESA. And this is similar, just providing a bit of disambiguation, because what used to be called ERM, European Refueling Module, is now called Lunar View, because there are also windows on that module to look through the windows. And what was called HLCS is now called Lunar Link, and what was called iHub is still called iHub. So, this is just for that. So let's talk about software. So we chose to use CFS on Gateway as the main software framework on most of the modules. It's used on, there is a list of the modules on PPE Halo. There are multiple instances of CFS just on the Halo module, on iHub or ERM, on the airlock module. So in total, there is, I believe, at least 7 different instances of CFS out there, if I don't take into account redundancies. And then, yeah, I forgot to start my control timer. And then, as you know, CFS is composed of several layers, CFE, then there is the platform support package, and which is provided for different computers, and we do have different computers on the Gateway. And then OSAL, operating system abstraction layer. Most of us use VxWorks and specific version of VxWorks, but we use multiple operating systems, in fact. Then there are 10 original CFS apps which we use, which were developed by Goddard. These are used on Gateway. And then on top of it, we have 13 specific apps which have been developed by the flight software team in Johnson's Flight Center. And these apps is 4 apps for TTE management and schedule, 3 apps for message routing and command verification, 3 apps to support crew displays, 1 app for shared data storage, and then 2 apps for management of crew health devices and payloads. So it's quite some number of applications used on different modules, on different operating systems, different computers. Then we use some data products, and I will talk about it later. We use the CCSDS electronic data sheets and XTCE. There is a common tool which is used to manage these data products, which is called Gateway Data Services. And part of it is also that we have Ghana, Gateway Assigned Numbers Authority, which contains all of these APIDs and assigned spacecraft numbers and spacecraft IDs, module IDs, processor IDs, and things like that, so that there are unique identifiers which are used by the software application. Then specifically on the ESA elements, we also have computers which are shared, the same computers which are procured and are used on different ESA elements. I will talk about it a little bit later, because then what comes in play is that they have the same bootloader, the same firmware, but perhaps for different operating system, there is different driver, because driver is specific for operating system. Then we use time-triggered Ethernet, and for that, there is some other software linked to that, because we have, I don't know, tens of TTE boards on the gateway, and those come with firmware, with drivers, again, with bootloader. And then we have some common tools. So this is just to demonstrate that there is a lot of software out there, and as I said, the central piece of it is CFS. For CFS, one thing which we do, which I find very, very important, is so-called common configurations. So basically, the flight software team, the Gateway flight software team, came with some configurations which are recommended to meet requirements which are shared by the modules. Sometimes it's a bit difficult because the requirements might be a little bit contradicting, but in fact, this allows to make integration and validation easier, because those app configurations have been already aligned with the requirements. And these are applied to both to the general applications and the gateway-specific applications. So at the bottom, it shows the process for every application. There is some initial configuration which is used in the initial release. Then for some identified applications, common configurations were defined. And then for every instantiation on each module, this common configuration which is proposed by the Gateway flight software team is considered in view of the module-specific configurations. So really, this thing has been very useful to make validation and integration easier, because the configurations are not sort of randomly chosen by the modules, but are aligned to some degree. I want to mention briefly the electronic data sheets which are used. So electronic data sheets is there is CCSDS standard which is called XML specification for electronic data sheets, which defines some data types and elements to describe software interfaces. And we use electronic data sheets on Gateway with some limitations. Some of the types are not used. Some of them have some sort of restricted use. And we added some new elements to do with Gateway autonomy, functionality, with tasks, with goals, and things which are not in the CCSDS standard and may be considered for an extension of the standard. Another standard which is used is so-called dictionary of terms. So it's electronic data sheets dictionary of terms, which allows to extend the specification by semantic attributes and extend those attributes. So this we use heavily on the gateway. XTCE stands for telemetric and command exchange, is used to describe structure of telecommand and telemetry packets. Again, it's a CCSDS standard, which is aligned with an OMG standard, which I think is a little bit older. So basically, how this works is that on the one hand, you have software applications which are represented by electronic data sheets, and then you have messages which are represented in XTCE. So so you can see that, for instance, there is telemetry defined, which contains variables, cabin pressure and cabin temperature, which are required variable by this vehicle system manager. So this is the electronic data sheet of the vehicle system manager. And on the other hand, that one provides variables which are in another telemetry, another piece of telemetry in the packet containing gateway phase and gateway mode. So basically, data like this, the data is mapped between provided and required interfaces, which allows verification that the data which is required and provided by different software applications is matching also the telecommands and telemetry which are defined in the system. So now a little bit more on the specific use on ESA elements. So as I mentioned before, ESA elements, which is IHAP, ERM, and HLCS, also use the same computers, which means also that they have the same interfaces, the same I/O boards. So there is also need to manage those interfaces. So there are apps such as 1553 Manager, I/O Manager, which are then common on those computers. And then on top of it, there is the same basic software and low-level software, common drivers, and things like that. So flight software architecture on each of these elements then is composed of two parts. One is common, which is the low-level part, and then there is mission-specific part, which is provided even by different suppliers. And that works in even different configurations. So as an example here, I mentioned that there is master-slave configuration on HLCS, because there are multiple computers out there, and while there is cold, warm standby, and warm monitoring on IHAP and ERM. So our supplier, Thales Alenia Space France, provides something called Flight Software Execution Platform, FSWEP, which is based on CFS, and that runs on every one of these computers. And then modules add to that a layer of application software, which is meeting mission needs. So then for different suppliers, such as Thales Alenia Space is providing application software for HLCS, while a company called GTD, our supplier, provides application software for IHAP. So overall, it looks like this. Yeah, so there you have the execution platform. You have dedicated low-level apps. You have a configurable set of NASA apps. And then you have specific application software. So this example is HLCS, but it looks the same on every other ESA computer. And this is basically an instance of CFS, which communicates with, in this case, Halo module instance of CFS, which communicates to another instance of CFS, which is at the level of the vehicle. This looks complicated, but I will not go into detail. But basically, it's to say that I mentioned Thales Alenia Space France, and as I said, they provide the flight software execution platform for us, but also applications for software for HLCS. But they also embrace model-based software engineering in such a way that the electronic data sheets are really used as electronic version of ICD. So really, they use it as a source to generate different artifacts, tests, test scripts, flight software code, to import flight software from NASA. They always first read the electronic data sheet. So they really use this the right way to build the system, to verify that the interfaces match and things like that. And this picture instead shows that that the module integrator, in this particular case, it's Thales Alenia Space Italy, who are the prime contractor for the iHub module, that they have to handle all of these data products coming from different sources. So in this case, it's there are data products coming from TAS France. They are, I think it's not quite visible there, but there are data products coming from GTD, which is the application software supplier. Then JAXA, the Japanese Space Agency, provides environmental and life control system for us. So there are data products coming from them. Then we need those data products also for verification and validation on test bench. We need to provide data products for operators. So in fact, this, in the end, there is a need for complex system to be able to merge those data products, verify them, make some exports, and provide what is needed to different stakeholders. So finally, to summarize my presentation. So we chose to, because there is a lot of software on the gateway, we chose to reuse reuse many instances of the same software rather than developing them separately for each module. And for this, we use CFS, as I said. And I showed also that the way CFS is built, it allows us, thanks to its modularity and layered structure, it allows us to deploy software which is provided by multiple suppliers and build consortium in such a way that the suppliers are responsible for different apps, and together they can build software which runs on the same computer. And these are positive points, so we definitely appreciate that, and we have been very happy with this. Obviously, doing that means that we have strong dependency on the CFS supplier, which is the team at JSC, and also that means that the modules then become a little bit dependent on each other as well, because if they need some functionality, then the other modules have to align with the release dates and things like that. So programmatically, that brings a little bit of complications because there are some dependencies. But we still believe that this is worth it, because the other way of doing it would be that we just develop, all of us, the same thing again and again, and there is no dependency. So, but definitely this is something to take into account. Now, technically, as I said, CFS worked for us greatly. It was deployed on different modules. It's used as the main data handling piece of flight software to handle a lot of software interoperability issues. So that's definitely a positive point for us. I mentioned the common configuration, which is really important for us to reduce integration and validation efforts. And then obviously one problematic point there is that sometimes it's difficult to create common configuration because the needs of different modules are slightly different. And then with certification, again, having pre-certified CFS helps us a lot because it reduces the risk and effort for our core software. And then obviously what we need to do anyway, that every module has to certify their own software product which they use on the module. And for sets and XTCE, again, for this kind of large project, you need some common data model. So we chose XTCE and sets, and this worked for us very well. And also, you need not only to have a standard for the data model, but you need some infrastructure which allows you to exchange the artifacts. And JSC provided to us also this one, so I think this works also very well. And the last point to say is that all of this is basically about data-driven flight software use. So all of these apps are designed in such a way that their configuration allows them to be reused in a different context. So I guess our message is that it's important that you design your applications to implement some sort of isolated function which is not necessarily mission specific and could be reused in different contexts, on different vehicle, rather than having to, rather than building apps which are very mission specific and cannot be reused. And obviously for this also sets was used to represent some of the configuration tables which are used in CFS and things like that. So here I would like to thank to the teams at ESA, Thales Alenia Space in France and Italy, NASA, Johnson Space Center. Two of the people are actually here, so thank you. And then GTD, which is the application software supplier. I listed many names there, but probably there were many more people involved, which I didn't list. And that's all from me. Thanks a lot.
Are there any questions?
Hey, so you mentioned how all of the different agencies developing the modules have to coordinate very tightly on how their software interfaces work together. But how do you coordinate with, say, the Orion flight software or the visiting HLS vehicles? Is there that strong of a contract with those providers as well?
That's a very good question. Yeah, because as you know, Orion has been existing for some time already. So there we have dedicated flight software interface, and so there the interaction is slightly different, and we worked on specific interface with them. So they are not part of this sort of gateway consortium. There are some standards which have, since we developed them, have become, they sort of moved from being gateway standards to become Artemis or Moon to Mars standards. But that's more at the level of, for instance, the use of secondary header in CCSDS packet or something like this, but not specifically to do with CFS because there is no CFS instance on Orion. There is, but it's on the backup computer.
We have a question online. Do you support the entire XTCE spec? And the second part of it is, did you consider any other interfaces for your mission DBs?
I was planning to say that we do not support the whole spec. Some of the sort of dynamic packets which are difficult for the MCC to work with, these packets we don't support these types. That was a good question.
Thank you. Any more? We can take one more in person.
Thank you, Marek. Who develops, maintains, and has custody of the electronic data sheets? Over.
So every flight software supplier has to provide electronic data sheet to come with the software. So for the final integration or for any integration, software has to come with sets. But there are tools to check, and there are some, there is some validation, etc. The tool I mentioned is already checking that the data sheet is using the types which are already registered there and things like that. There are multiple steps by making, to make sure that that it's corresponding. And it's not so difficult to check it against the source code and things like that. So there are tools for that.
Thank you very much. Give it up for Marek.